This is the video for the solutions for integration from calculus revision. So some straightforward integration there in question 1. In the first question I have no limits, just watch out for that, so it's indefinite integrals. So remember your rule is up the power and divide by the result. And because I've no limits, I mustn't forget the plus c on the end. I can tidy this slightly, and there's my final result, so nice and straightforward. On to part 2, I've got an exponential term and I've got a trig term, so you need to have the log tables to hand here for this. For the exponential term, I leave it as it is, and then I divide by the derivative of the power. So I'm differentiating 2x to get 2, and I'm dividing by that. Cos differentiates to give minus sign, so just watch out because there's already a minus in this case. So I've got plus 3 sine 2x, but then of course I must divide. Oh, actually, apologies, I've just realised. Cos differentiates to give sine, so actually no sign change required there. And then I have to differentiate the angle and divide by the result. And then of course it's an indefinite integral, so that plus c has to go on the end. I can do a little bit of tidying again if I like to get this slightly simplified version of the answer. Okay, on to part 3 then. We're looking to integrate. This time we do have limits. It's a pretty straightforward integration in this case. My algebraic term is just x cubed over 3. And e to the x is nice and straightforward. It's just going to end up being e to the x. I have to incorporate the limits into my answer, so I'll sub them in and subtract. It's absolutely fine to keep exponential terms in that format in my answer, so I don't really have to go to the calculator for that. I might do that for the fractions though. And there's my final simplified solution. Okay, so question 2 then, it gives me a function first of all and says find f dash x. So actually I am differentiating to begin with here, and I want to then use what I've got to integrate a slightly more complicated problem. So I can see in the function I've got multiplication of terms, so I'm going to have to use product rule. So I've got my u and my v written down here. So I differentiate both of those. There's my product rule just to remind me how it works again, and I can tidy that up slightly. Okay, so I've completed my first step of the question, which is to differentiate, and I now want to integrate 6x e to the 2x dx, which I can actually see was part of my answer for my differentiation. Now, of course, there's multiplication happening in here between two terms, but I don't have a rule in integration to cope with that. So I'm going to see what happens if I just integrate all of this here, because don't forget, integration is reverse differentiation. So if I have this as a result of differentiation, then if I integrate this, it'll bring me back to the original function again. So I differentiated this expression to get this expression. So if I integrate this, it'll bring me back to the beginning. But the question doesn't ask me to integrate the whole thing. It just says integrate that bit. So I'm going to split up my integral here. And I'm going to isolate this guy that I want to find, according to the question, on the left-hand side and get everything else on the right. Okay, so now I can find what the integral of 6x e to the 2x is if I just figure this guy out, and maybe I might need to tidy up a little bit. I'll definitely need to include a plus c at the end because it's an indefinite integral. Okay, so what am I going to get when I integrate this guy then? Well, again, it's an exponential term, so I'm going to differentiate its power and divide by the result. And then I stick my plus c on the end. And actually, I'm completely finished now. That's the answer to that question. On to question 3. Particle is set in motion. Its velocity is given. What is the distance travelled by the particle? So we know already from the end of differentiation as well that distance, speed and acceleration are all linked. And I know that if I'm going from distance towards speed and acceleration, I'm going to differentiate. And if I want to go back in the other direction, I'd have to integrate. Again, because differentiation and integration are opposites of each other. So I've got velocity. So velocity is just in the word for speed. And I want to get back to distance, so I'm going to have to integrate. So let's see, what am I integrating? So I'm integrating my velocity expression, 3t squared. And the variable is t, so I'm doing that dt. When I integrate that, it's 3t cubed over 3. But now actually there's a bit more in the question. It's not an indefinite integral question. They actually say to me that I want to find the distance travelled by the particle in the first 2 seconds. So imagine I've got a stopwatch going at the beginning. It starts at 0 and I want to stop it after 2 seconds. So I'm actually getting this value between 0 and 2. I can make life a little bit easier for myself here. Just knock off those 3's and then sub in my value. And I get an answer of 8 meters. And I know that it's meters is the unit for distance here because first of all, it's distance. And second of all, meters were mentioned in the velocity expression. On to question 4. I'm asked to find an area. So I want to find the area bounded by this curve, the x-axis and the interval AB, where A and B are the roots of f of x. So A and B are those 2 points there. So to be able to figure the answer out, I have to actually start off by figuring out what those guys are. And then I'll be able to proceed to find the area. So I know with cubics there's a little bit of guesswork involved initially. I'm going to have to find a value that I can sub in that's definitely a root. I'll start with f of 1, and actually in this case that works out quite nicely for me. So x equals 1 is definitely a root. In fact, I can actually see from the diagram that x equals 1 is a repeating root. So I could take a risk at this stage and I could just state that, or if I prefer to be a bit more confident about it and not take the diagram kind of too literally, I could work that out as well by figuring out the other roots from the function. We will actually find in this case that x equals 1 is a repeating root. You can see that the x-axis there is a tangent in the diagram. In any case, to get the other roots, I'm going to have to do a little bit of algebraic division. But first of all, I need a factor. So if x equals 1 is a root, x minus 1 is the factor. So I'll divide that into the function. So I'm going to use an array. In go the first and last terms. There's my x minus 1 factor. X into x cubed goes x squared. Minus 1 into plus 2 goes minus 2. And then I can fill in these boxes here. Minus 1x squared and minus 2x. And then I'm going to go back and refer to the original cubic in order to figure out what the missing boxes are. So if I look at my original cubic, there's no x squared terms. So I want to get rid of this guy. I can do that by putting in a plus 1x squared, and then I want minus 3x, so I'm at minus 2 if I need minus 1x here. So I can get my middle term here of my quadratic factor, so plus 1x. I have to factorize then that quadratic to get all of the roots of the cubic, and we get x plus 2, x minus 1. Oh look, we have that x minus 1 again. Yeah, that was definitely a repeating root because I've got a repeating factor as well. So definitely the only roots that I have to worry about are minus 2 and 1. I'm going to fill them in there to the diagram so you can see them as well. And then I'm going to integrate to get area. So I'll just integrate, and it's a pretty simple integration. Don't forget to include your limits, and then just sub those in. And then off to the calculator, and my answer comes out as 6.75 units squared. And of course the answer was positive on the calculator because the area is above the x-axis. Next, I want to find the area enclosed by the function and the x-axis. Now this time they haven't given me a function, but I can see that it's a quadratic. And I can see that it has roots at 1 and minus 4, and I can also see the y-intercept. So I've got plenty to be able to make this quadratic. I've got my roots, x equals minus 1 and x equals 1. Sorry, x equals minus 4 and x equals 1, which means I've got factors x plus 4 and x minus 1. And when I multiply this out, I'm going to get x squared plus 3x minus 4. And I can see that my y-intercept matches, so I'm happy with that. I want to find the area enclosed by the function and the x-axis. So I am trying to figure out the area under here, which will be negative because it's underneath the x-axis, between these limits. And now I just go to substitute in. Just be careful of all those brackets. Particularly watch out that you put a bracket around any negative values that you put in. I get a negative answer in this case. I'm not surprised by that because of the fact that it's underneath the x-axis, but of course area is positive. So I'll give my answer as 125 over 6 units squared. Now, it's perfectly fine to leave this answer as an improper fraction. In fact, it's probably better. You'll see it actually given that way a lot in both the back of the book and in exam paper solutions. Okay, so finally on to question 6 then. In question 6, they're looking for an average temperature. So the minute you see the word average in there, that's a big hint that you're looking at average value in this question. And of course, we have a formula for average value, and that's just the generic version of the formula there. And so I need to figure out what I'm integrating and what my limits are. So they're giving me a function, so it's pretty clear that I'm integrating this function here. And my limits are going to be kind of figured out from this last sentence here, during the period from 9 a.m. to 9 p.m. And if I look back here in the previous line, it says that in a certain city, the temperature in T was worked out T hours after 9 a.m. So that means 9 a.m. Well, that's 0 hours after 9 a.m. because it's when the clock starts, if you like, and 9 p.m. is 12 hours after. So those are going to be my limits. So I've got 1 over b minus a, my limits getting subtracted, there are my limits filled in, and I'm going to integrate this particular function here. So I'll just leave the 112 sitting out in front. 50 is going to integrate to give me 50t. So now I'm going to integrate this term here with the sine. So the 14 can stay put. Sine integrates to give minus cos, and I must differentiate the angle and divide. Now when I'm differentiating that angle, just bear in mind that the t in there is the variable, okay, and pi over 12 is its coefficient. So if you think about if I had 2t, it would differentiate to give me 2. If I had 10t, it would differentiate to give me 10. So I just hang on to the coefficient of the t. So when I differentiate this, I'm going to end up with pi over 12, and then I have to include my limits. Notice in this question that I've got pi in the angle, so I want to have my calculator set up, in this case, in radians, because pi is indicating that the angle is in radians. So make sure to adjust that before you begin to calculate. And now I'm going to start subbing in my values. Make sure there's a bracket all the way around the outside so that the 1/12 is applying to everything. And then take a deep breath and type the whole thing in. And I'm getting an answer of 58.91 degrees, and that is degrees Fahrenheit as well. Just bear that in mind. Now, with a question like that, I'd nearly advise typing that in a couple of times. And if you wanted to, you could do a bit of cancelling out before you began to type in. So you cancel out your 12s there, for example. This is all going to be a 0 because it's multiplying by 0 inside in the angle. This guy is going to be a 0, so you can kind of tidy that up a little bit if you like. Make sure when you're typing in this big clunky fraction here that you press the fraction button before you start on the 14, just to make sure that you don't run into difficulty after the fact, as it were, and make sure that for every bracket you open, you close a bracket.